friends, welcome to my YouTube channel Easy Mathematics. In this video lecture, we have started the counting technique, which is the part of discrete mathematics. Initially, fundamental counting principle. The fundamental counting principle is a mathematical rule that allows you to find the number of ways that a combination of event can occur. If there are m number of ways for one activity, any one activity, and n number of ways for second activity, then there are total m into n number of ways for both the activity occurs. For example, there are two questions given. Question number 1, which have three options. Option number 1, A, 2, B and C. In question number 2, there are four options. 1, 2, 3 and 4. Now a student is supposed to choose one question from the question number A and one question from the question number B. In this choice, how many possible number of ways of the different combinations or the different choices are there? So from the first question, out of these three, anyone can be chosen. So there are three options. In the second one, four options. Among these four options, anyone can be chosen. So for if suppose someone chosen this first one, so with this, either this one or this one or this one or this one. So these four combinations can be possible. So for one choice of question number A, there are four possibilities. Similarly, someone if choose the question number B, so with B, he or she may choose 1, 2, either 3 or either 4. So there are again four possibilities. For C also, for one choice, any 4 out of these 3, these 4 can be selected. So total number of choices can be possible is 4 into 3, that is total 12 number of ways are there by which the different choices can be possible. Now, there is the counting principle, means there are two type of things which we should know. One is the permutation, another one is the combination. So what is permutation? If different arrangements made by taking some or all from a given set of things are called the permutation. Whereas the combination is what? Combination is a set of collection of objects where order does not matter. So permutation is what? Permutation is the arrangement of things. And combination is the selection of objects. In case of permutation, if total n number of objects are there and out of n objects, if we want to choose any r object, then out of n we should choose any r object in n factorial divided by n minus r factorial ways. Whereas in combination, out of n, if our choice is any r object, then its formula is n factorial divided by r factorial into n minus r factorial. So for example, if we want to understand about the permutation and combination and its differences is that, suppose there is a queue and in that queue total 10 number of students are there. Among these 10 number of students, if we want to choose any 3 students, then there are possible NCR number of ways, because out of n we are supposed to select any 3. But if we want to arrange 3 out of 10 students, we should select at first 3. After that we should arrange them. That means if there are 10 students and suppose 1, 2 and 3 students we have chosen, then 1, 2, 3, 3, 2, 1, then 2, 1, 3. These all are the different arrangements among these 3 students. So only choice for the combination, and after choice, when we arrange them, then it is the permutation. That's why here NCR means n factorial divided by r factorial into n minus r factorial. That we can write as, if we write 1 by r factorial separately, then the remaining is NPR, just the same thing. So we can say NPR is equals to r factorial into NCR. So this is the main difference between these two. Now, the object can repeat it any number of times. That means if suppose I have A, B and C, and I want to arrange or I want to form a word of 3 letters. So I can choose in the first position A, B or C, anything. Now in the second position also I can choose A, B, C, anything. In third position also I can choose A, B, C, anything. So that our letter is AAC or AAA or AAB. In this way anything can be possible. That means repetitions can be allowed. If these repetitions can be allowed, then the total number of permutation is n to the power of r factorial. So 3 positions are there and 3 choices we have. So this is the total number of way by which we can arrange in these 3 letters. So now it is the combination for the selection is there. That means repetitions for one object again and again is not possible, because once you select one object, then it is done. There is no other option to select the same object again. Now in the permutation, we have one more thing, that is the number of permutation of n objects, in which p objects are of one type, q objects are of second type, and r are the third type of objects, r times. Then the different type of permutations are n factorial divided by p factorial into q factorial into r factorial. For example, suppose we have the set, there the elements are x, y, z, then a repeated 3 times, b repeated 4 times and c repeated 5 times. If we want to take the permutation of these 15 arrangements, that means how many ways these 15 things can be arranged, for that the total number of arrangement in the permutation, usually it is 15 factorial, but as a is repeated, then this 3a you may write anywhere. So the same thing, that means swapping, that means one a is written here, another a is written here, means if we just replace their places, then it will remain the same thing. There will be no change in the combination. That's why for the similar type of thing, we just divide it by this number of factorial. That's why a repeated 3 times, so that we divide it by 3 factorial, b repeated 4 times, that's why we divide it by 4 factorial, and c repeated 5 times, so that we divide it by 5 factorial, and as a resultant we will find out that much number of permutations are possible. So this is the differences between permutation and combination. We know what is permutation. Now it is the restricted permutation. That means few restrictions are imposed in the situation. That time what should be the formulas will be there in the permutation that we will discuss in this lecture. So suppose r number of objects are to be taken from total n different objects given. Among these r objects, m particular objects are never included. If it is so, then the formula is n minus m pr. For example, suppose 1, 2, 3, 4 and 5 fruits are given. Among these 5 fruits, orange and lychee will never be included or taken. So from the remaining 3 fruits, we are supposed to take any 2. So if it is so, so the remaining 2 means here the 5 minus 2, so the remaining are the 3 number of fruits. With that, we are supposed to choose any 2. So this is the total number of permutation, which is 6. Here, in the first choice, we suppose take mango, and the second choice, we suppose take the apple. So that in the second set, we can choose first apple, then mango. Then two type of combinations are there. Then mango, banana, banana, mango, apple, banana, banana, apple. So these are the total 6 different choices, and this is the total number of permutations which we can do in this situation. Next situation is the same n number of total objects are there, and r objects are to be chosen. Among these r objects, n particular objects are always present. In the previous one, some objects are always absent, and here the some objects are always present. That time what the formula? This is n minus m p r minus m into r p m. So what we will do? When some objects are always present, then what we will do here? Suppose the previous example, 5 total different fruits are there, and let banana is always present there, so that remaining number of fruits are 5 minus of 1, then p, and our total number of choices are suppose same 3. So out of 3 banana is always there. That's why out of 3 banana is always there. So the remaining 2 things we are supposed to select from the remaining 4 fruits. Now here the R is 3 and P and M is 1. That means banana is always selected, and that can be chosen in a row. There are total 3 positions, no, 1, 2 and 3. So banana can be chosen at the first place or second place or third place. For this arrangement, this permutation is there. So this is when M particular objects are always present. Now the next situation is M particular objects are placed in M given positions in a given order is n minus M, P, R minus M. Here this term is absent. What does it mean? Here it is given that the places are fixed for the chosen particular element. So M particular objects are placed in M given positions. So for example, suppose this one is the set where total 6 numbers are there. Among these 6 numbers, suppose 2 and 3. These 2 numbers are fixed, and these 2 numbers are fixed in the positions also. So this is the fixed thing. So the remaining 2, our total choice is 4. Out of these 6, 2 is fixed. So the remaining positions are 2. So out of these 4, any 2 we can select and we can set up. So according to the formula, it is 6 minus 2p. Here 4 minus 2. This is the total number of permutation, which is 4p2 or 4 factorial divided by 2 factorial. That is 4, 3. That is 12. Next is M particular objects are placed in M given positions in any order. Previously the orders are fixed. Now here no orders are there. That means 2 places may be restricted for 2 particular elements, but they can exchange their places. So again, if we consider the same example and suppose 2 and 3 are the fixed, so that time if we place 2 here and 3 here, 2 here and 3 here, then this 2 and 3 can exchange among themselves. According to these situations, the formula is m factorial into n minus mp r minus m. Next situation is M particular objects occur together. Its formula is R minus M plus 1 into N minus M P R minus M. Suppose the same example we have chosen, and here 2 and 3 are the objects which are always coming together. 2 and 3 are always coming together means either this one is 2 and this one is 3, or this one is 2, this one is 3, or this one is 2, this one is 3. So these are the 3 different positions. So the remaining 2 can be combined is the N minus M P R minus M, and here this one is R minus M plus 1. That means here total out of 4 situations, out of 4 positions, we have the 3 different choices to place the fixed elements. So this is the formula. One more thing is the circular permutation. That one is very important. An arrangement of objects round a circle is called the circular permutation. So that its formula is n minus 1 factorial. If it is not a circular permutation, a linear permutation is there, then if n objects are there and all these objects if you want to arrange, then its formula is just n factorial. But if it is circular, then it is n minus 1 factorial. That is because suppose this is the 8 objects are given in a circular manner. Now if we fix this object, after fixing this one, we can arrange the remaining 7 objects. So there are all different possible combinations by n factorial ways. That means here total n. If we fix any one, then the remaining is n minus 1. Then we can arrange the remaining n minus 1 in n minus 1 factorial way. Now this arrangement may be of 2 types. One is the clockwise and another one is the anti-clockwise. If clockwise and anti-clockwise both are same, then it doesn't matter. Then the total thing is, if this is same in clockwise and anti-clockwise, then what happens? Clockwise and anti-clockwise for, we have the same combinations, and that's why our formula that time is half of n minus 1 factorial. Because if we take the clockwise, suppose this is one of the arrangement, and if we just exchange 2 to 8, then 3 to 7 and 4 to 6, then it is definitely a different arrangement, but in the same sequence. That's why if clockwise and anti-clockwise arrangements, it doesn't matter, then its formula is this one. For example, if we consider the bits of a chain is there where all bits are same. That time the circular, that means clockwise and anti-clockwise, doesn't matter. These are the few important aspects of the permutations. Now next chapter, it is the combination. So combination is NCR, that we know. There are some properties, some important properties are there. So the first property is NCR is equals to NC n minus R. Remember, R is always lies in between 0 to n. So all these properties we can verify by using this triangle. This is called the Pascal's triangle. So just observe this triangle very carefully. First is 1, then it is 1, 1. This position is vacant. Then 1, 2, 1, 1, 3, 3, 1. So in this way. If we take the middle elements only, then this we can say as the mirror. And you just observe all these elements and these elements just in the symmetric manner. Now we can say these all are the, depending upon the n and r, the coefficient of the combination. How it is? Here the first element is 1. So we can say here n is 0, and definitely then r have no choice other than the 0, and the formula is NCR. Here 0 C 0 means obviously it is 1, because the formula we know, that is n factorial divided by r factorial into n minus r factorial. So it is 0 factorial is 1, r factorial is 0 factorial is 1, n minus r means 0 minus 0 factorial, that is again 1. So the total value is 1. That's why this coefficient we have written here. So we can say this one is the 0 C0. Next, the second one. That one we can say here n is equals to 1. So r have two options, either 0 and 1. So that according to this value is 1C0 and this is your 1C1. So 1C0 means 1 factorial by 0 factorial into 1 factorial. So it is 1. Similarly this one. Next one, it is here n is equals to 2. So that it is 2C0, this is 2C1 and this is 2C2. So look, in this way, if you just go down, then you will find out accordingly n will be increased and accordingly the different r values. So that here one more thing is very important to observe, that if you just take this one as the mirror, then the corresponding distance elements are same. That's why we can say NCR is equals to NC n minus r. So for example, if we consider this one, then here the n is equals to 4. N is equals to 4 means the first element is n 4C0 and the next element, the last element is 4C4 and these two are same. Next 4C1 and 4C4 minus 1, that means 4C3. So 4C1 is this one and 4C3 is this one. So these two are same. That's why this one is. The next property is NCR plus NCR minus 1 is equals to n plus 1 CR. So again come to this triangle, and here you can choose any two consecutive value in this triangle in the same line. Suppose we choose this one and this one. After choice of these two, you just add these two. After adding these two, you will find out in the next line the corresponding element. You may choose any two here. Suppose this one and this one is chosen, and you will find out the summation is in the next line. That means what? If we consider this is the fourth row, n value is 4, and here it is the n value is 5. Here the n value is 5. So in the fourth row it is n, that is 4c, it is 4c1 and it is 4c2. Its summation is 5c2. Is it now? So that's why we can write NCR plus NCR minus 1 is equals to n plus 1 CR. It always happens. Now one very much important thing which I can disclose is 1 means we can write it is as 2 to the power of 0. Then 1 plus 1, that is the 2. We can write this one as 2 to the power 1. 1 plus 1, 2. Next it is 1, 2 and 1. That we can write as 2 to the power of 2. So look, 2 to the power 2 is 4 and 1 plus 2 plus 1 is 4. Next one is 1, 3, 3 and 1. And if we add all these, then we will find out it is 2 to the power 3, that is 8. 4, 4, 8. Next one is if we add all these values, then we will find out 2 to the power 4. Similarly, this one is our 2 to the power 5, this is 2 to the power 6 and so on. That's why we can write any this coefficients or any these combinations for n where r is the total number of choice or n is the total number of choice, that if we add all these, then we will always find 2 to the power n. These are basically the really of the binomials. So definitely we discuss the binomial in our next video lecture, but before that some more properties on the combinatorics. So in the previous way, the permutation form, we have some restricted permutations. Here also some restricted combinations are there. So among them, if the number of combination of n objects taken are at a time in which m particular objects never occur, then the same way the formula is n minus m CR. And for m particular objects which it is always occurs, the formula is n minus m CR minus m. So this is the different combinations. Now in the next lecture, we do some problems on permutation and combination. Now that is the problems related to permutation and combination. So the first problem is how many different signals can be made by 5 flags from 8 flags of different colors. There are total 8 different flags of different colors. Among them, we want to make a signal of 5 flags. So it is very obvious. It can be 8P5. So this is the arrangement and its value is this one. In the next problem it is, in a class of 10 students, there are 3 girls, A, B and C. In how many different ways can they be arranged in a row such that no 2 of the 3 girls are consecutive? So no 2 girls are consecutive means 10 students are there, among them 3 girls. That means total 7 boys are there. So 7 boys are there means they can be arranged. The 7 boys can be arranged in 7 factorial ways. So now 7 factorial ways means there are 1, 2, 3, 4, 5, 6 and 7 total possibilities of the arrangement. So 7 places are there to arrange the boys. Now the 3 girls are there, and for these 3 girls, how many different places are there to place those girls? So the first place we can place a girl here or here or here. So these are the all possible ways where the girls can be arranged. So these are how many numbers? 1, 2, 3, 4, 5, 6, 7 and 8. So there are total 8 positions are there where we can place these 3 girls. So in 8 positions, 3 girls can be placed in 8p3 ways. So the total number of arrangement is 7 factorial into 8p3 factorial. The next problem is how many words can be formed using the letter A thrice, that means A occurs 3 times, the letter B twice, B occurs 2 times, and the letter C occurs thrice. So this is A, B and C. So the how many different letters we can form? So here total 1, 2, 3, 4, 5, 6, 7 and 8 options we have. So N is equals to 8. Now A repeated 3 times. So that is 3, B repeated 2 times and C repeated 3 times. According to the formula, it is 8 factorial divided by 3 factorial, 2 factorial and 3 factorial, and hence the result. Next problem is, in how many ways 5 rings can be in how many ways 5 rings of different types can be worn in 4 fingers. There are 4 fingers and 5 rings. How many ways we can form it? So look, the first ring can be worn in any one of the 4 fingers. So there are 4 ways of wearing it. Similarly, each one of the other rings can be worn in 4 ways. So this is the repetition of the rings can be possible, so that it is n to the power r, or it is 4 to the power 5 ways are there. Now the next question is, a new flag is to be designed with 6 vertical strips using 4 colors. In how many can this be done so that no 2 adjacent strips have the same color? So the answer for any one of the 4 colors can be used to color the first strip, and the second strip can be colored using 3 colors excluding the first one. The third strip can also be colored using the 3 colors excluding the color of the second strip, and so on. Hence, in this way if we proceed, then in the first situation we have the 4 options. In the second, third, fourth, fifth, remaining all we have total 3 options. That's why it is 4 cross 3 to the power 5, and this is the result. Now, how many committees of 4 persons with a given chairperson can be selected from 10 persons? So, since the chairperson can be any one of the 10 persons, therefore, he can be selected in 10 ways. The remaining 3 persons are to be selected from the remaining 9 persons. This can be possible in 9p3 ways. Hence, the required number of committees are 10 for the first choice and the 9p3 for the remaining 3 choices. That's why this is the result. Next it is, out of 7 consonants and 4 vowels, how many words can be made, each containing 3 consonants and 2 vowels? 7 consonants given, 4 vowels given. We are supposed to form a word where 3 consonants are there and 2 vowels are there. So, 3 consonants can be chosen from 7 consonants in 7C3 ways, and 2 vowels can be chosen from 4 vowels in 4C2 ways. Now, the number of combined group each contains 3 consonants and 2 vowels is 7C3 cross 4C2. Hence the result. But again, each of this group contains 5 letters which may be arranged among themselves. That's why these 5 letters can be arranged 5 factorial ways. So this is the combination, and after that this is the arrangement. That's why the total number is this one. And the next question it is, in how many ways a committee of 5 members can be selected from 7 men and 5 women, consisting of 3 men and 2 women. Just exactly the previous one we will do. The 3 men can be chosen from 6 men in 6C3 ways, and 2 men can be chosen from 5 women in 5C2 ways. That's why the total number is this one. Here the permutation is not there. That means only the committee is forming. That's why this is the discharge. In previously, after formation of the word, its arrangement is also important. That's why this one is multiplied. Next one is, in how many ways can 5 different subjects be arranged in 6 periods of a class? So, for that, if we arrange 5 subjects in 6 periods, then one subject must be kept twice. If a particular subject is arranged twice, then they can be arranged in 6 periods in 6 factorial by 2 factorial ways, because 6 is the total number of periods, and there one subject repeated 2 times. That's why 6 factorial by 2 factorial, and this is the total answers. Therefore, 5 different subjects are arranged in 6 period of classes in 5 cross 6 30 number of ways, because 5 different subjects are there. We can do this same thing for the all 5 subjects. That's why 5 should be multiplied here. Next and the last question is, here is, in how many ways can a 6 beads of different colors be arranged to form a necklace? So if no restriction is made between the clockwise and anti-clockwise, then the necklace means it is the circular arrangement. Then the number of different circular arrangement is 1 by 2 n minus 1 factorial. So that it is 5 factorial by 2 factorial. Hence it is 60. So this is the problems on permutation and combinations. There are so many more problems exist. So in our next lecture we discuss on the binomial theorem, which one is the continuation of the combinatrix or the coefficients, you can say. Now it is time for the binomial theorem. So the statement for the theorem is, if x and y be two variables and n greater equals to 0 be any integer, then x plus y to the power n is equals to summation of NCR x to the power r y to the power n minus r. And if we expand it where r is 0 to n, so when r is equals to 0 we will find out NC0 x to the power 0 means 1, then y to the power n. So it is the first term. When r is equals to 1, then we will get NC1 x y to the power n minus 1. And likewise the remaining terms we will find out. Now if we want to prove this, then for the proof, here we are supposed to prove x plus y to the power n is equals to this expression or the summation. So now we can write x plus y to the power n as x plus y into x plus y into x plus y in this way up to n terms. If x is chosen from r terms, then y must be chosen from the remaining n minus r terms. We can take the first r terms or r factors from here for the coefficient or for the power of x, and the remaining factors we can choose for the power of y, so that we will find out the terms of the kind x to the power r, y to the power n minus r. Again, r terms can be selected from n terms. Here total n terms are given. So from these n terms, r terms can be selected in NCR ways that we know. So that means x to the power r, y to the power n minus r appears NCR times. Hence we can write here x plus y to the power n is equals to NCR x to the power r, y to the power n minus r. And all such terms we will find out if then we take it in the summation, where summation is tending from 0 to n. This is our binomial theorem. Now, if n be a positive integer, then 1 plus x to the power n is equals to, we can write summation of r is equals to 0 to n, where NCR x to the power r. Here we consider instead of y as 1, then 1 plus x. Now if we expand, then the same thing, we just substitute r for 0, 1, 2, 3 and we will get this series. Now there are few more general series which we use very often. So among this series, one most important is the 1 plus x whole to the power minus n. N may be 1, 2, 3, 4, anything. If it is so, then according to the binomial, we will find out this series as summation r from 0 to infinity, remember, because these all are the infinite series. Now minus 1 to the power r, then n plus r minus 1 cr into x to the power r. If we expand it, then we will find out so. Instead of 1 plus x to the power minus n, if it is 1 minus x to the power minus n, then we will get the same type of series, only the alternative plus minus sign will be not here. That's so why we will get this series. For specific, if we consider n is equals to 2, then we will find out 1 plus x to the power minus 2 is equals to 1 minus 2x plus 3x square minus 4x cube plus dot 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 and up to infinity. If it is 1 minus x to the power minus 2, then accordingly all terms are positive. Instead of 2, if n is equals to 3, then we will find out this 2 series. Similarly, n is equals to 1 for we will find out the infinite series. For n is equals to 4, also we can find out the infinite series, and likewise we can construct any such kind of binomial series. If the power is positive, then it is the finite series, and if the power is negative, then it is an infinite series. Now there are few problems related to the binomial. So now the first problem is, find the coefficient of x to the power 5 in the expression 4x plus 5 to the power 15. Now 4x plus 5 to the power 15, here total 15 factors are there, so that we can write 4x plus 5 to the power 15 is equals to this way. There are total 15 terms. So now our target is to find out the coefficient of x to the power 5. That means from these factors, these 15 factors, we are supposed to choose any 5 factors. So if we choose any 5 factors, then we will definitely find out the coefficient of x to the power of 5. And among these 15 factors, if we are supposed to choose any 5, then there are 15C5 such ways. So now if we substitute according to the binomial theorem, then corresponding to the term x to the power 5, that means corresponding to the coefficient of x to the power 5, we will find out 15C5. Then x means here 4x to the power 5, and then 5 to the power n minus r, that means 5 to the power 15 minus 5. If we simplify, then we will find out 15C5, 4 to the power 5 and 5 to the power 10 is the coefficient of x to the power of 5. Similarly, one more problem is given. So the determine the coefficient of x to the power 5, y to the power 10 in the expression of x plus y to the power 15, and find the coefficient of x to the power 5, y to the power 3 in the expression of x plus y to the power of 8. So now for this expression x to the power 5, y to the power 10, here the expression is x plus y to the power 15. So 15 means 10 plus 5, 15 total. Always in a binomial, you can choose any term. They are the variables for, you just choose the powers of the each variables. After addition of these powers, you will find out ultimately the total power of the expression. Definitely it has to be same. Likewise in the second problem, 5 plus 3 means 8, that's why the expression is chosen from x plus y to the power of 8. Now the coefficient of this one in the first term, it is out of 15, we should choose any 5 term for the x to the power 5. So it is 15C5. And definitely then 15C5 x to the power 5 you will find out into y to the power 15 minus 5, that is 10. So the coefficient is this one. Similarly, in the second expression, the coefficient is 8C5, and that is the total answer. Now one more question. It is the determine the coefficient of x to the power 5, y to the power 4, z to the power 3 in the expression x plus y plus z to the power 12. Here, instead of the 2 variables, there are total 3 variables, x, y and z, and the total sum of the power is 5 plus 4 is 9 plus 3 is 12, that is equals to this power. Now we can assume x, y plus z is equals to u, so that we can express this expression as x plus u to the power 12. So x plus u to the power 12 is expressed in this way, and here the coefficient of x to the power 5, if we want to find out, then it has to be 12C5. So 12C5 x to the power 5, and definitely u to the power 7 is the remaining part. Now in the u to the power 7 means x plus y plus z to the power 7. In this expression, we are supposed to find out the coefficient for y to the power of 4, which we will find out as 7C4. Then it is y to the power 4 and z to the power 3, very obvious. Hence the total coefficient corresponding to this term is, we will find out 12C5 into 7C4. So now if you simplify, then it is 12 factorial by 5 factorial into 12 minus 5 means 7 factorial into, for this one 7 factorial, 4 factorial, then 7 minus 4 is 3 factorial. If we simplify, this 7 factorial cancel out. Hence it is 12 factorial divided by 5 factorial into 4 factorial into 3 factorial. So that's all for the binomial. Hello friends, this is the most wanted lecture on pigeonhole principle for you. So what is pigeonhole principle? The statement is, the pigeonhole principle states that if n pigeons are put into m pigeons, if n pigeons are put into m pigeonholes with n greater than m, then at least one pigeonhole must contain more than one pigeon. This is very obvious. If suppose there are total 15 number of pigeons are there and total 9 number of pigeonholes are there. So 15 pigeons are there, 9 pigeonholes are there. So we can accommodate first 9 pigeons in the 9 holes. After that, the remaining 15 minus 9 means the 6 pigeons which are supposed to accommodate in this 9 holes only, so that at least 6 holes we will find out which we have to accommodate 2 pigeons in each hole. So this is the pigeonhole principle. Now it is the generalized or extended pigeonhole principle. So if there are n pigeons and m pigeonholes where n greater than m, then one of the pigeonhole must contain at least n minus 1 by m within the box function plus 1 pigeons. I hope you know the box function, but still let me tell you what is box function. That is where box x means the largest integer less than x. So largest integer less than x means if in a box function there are 2.5, then its value should be 2, as 2 is the largest principal not exceeding this value. Now according to the generalized pigeonhole principle, the formula is n minus 1 by m plus 1. So if the same problem we consider, the 5 pigeons are there and 9 number of holes are there, then n minus 1 by m means its value is 15 minus 1 by 9 means it is 14 by 9. Its value is 1.66. From the box function, its definition, the value is actually 1, because 1 is the largest integer which is not exceeding 1.66. Hence, one of the pigeonhole must contain at least n minus 1 by m plus 1, that is 1 plus 1, 2 pigeons. So that is the pigeonhole principle. Now its proof is also required. So for the proof for the pigeonhole principle, it is very easy. So initially we assume that every pigeonhole will contain no more than n minus 1 by m pigeons. So the total number of pigeons in m pigeonholes will be at most m into n minus 1 by m within box function. This is the number of pigeons for each holes, so that m holes are there, so the total number of pigeons should be m into the number of pigeons in each hole. Now m into n minus 1 by m, it has to be less than equals to m into n minus 1 by m if we just omit the box function. So that one is equals to m cancel out and that one is equals to n minus 1, which is a contradiction because there are n pigeons. This implies that our assumption is wrong. Hence, if there are n pigeons and m pigeonholes where n is greater than m obviously, then one of the pigeonhole must contain at least n minus 1 divided by m plus 1 pigeons. And this is the proof. So simple proof, just the simple logics you are supposed to include. Now regarding the pigeonhole principles, there are few problems. The first problem: how many people, at least in a group of 110 people, have the same last initials? Here given total number of people are 110. In English word, we know there are total 26 alphabets are there. So M value is 26 because the last initial definitely among these 26 letters. Hence, according to the pigeonhole principle, n minus 1 by m plus 1, if we apply this formula, we will find out that its value is 5. So, we can say there are at least in a group of 110 people, 5 people have the same initials, the same last initials. Similarly, the second problem is so that at least 2 people out of 13 must have their birthday in the same month when they are assembled in a room. So here given total number of people are 13. In a month in a year there are total 12 months. So m is equals to 12. According to the principle we will find out this value is 2. Hence the answer is there are 2 pupils which have the same month when they are assembled in a room. They have the same birthday. Now the next question is so that if 10 colors are used to print 201 houses, at least 21 houses will be of the same color. So total number of houses are 201 and total number of colors used are 10. So according to the pigeonhole principle, we are supposed to use here 20 plus 1 means 21 21 are the colors which have one. So at least 21 houses will be of same color. Next question is how many people must have to guarantee that at least 9 of them will have birthday in the same day of a week. So there are n number of people that we don't know how many people are there. And in a week there are 7 different days. So according to the principle that value should be 9 because it is given that at least 9 of them will have the same birthday. So according to the principle, if we substitute n is equals to 7 and now we simplify, then it is n minus 1 by 7 plus 1 is equals to 9, which implies n minus 1 by 7 is equals to 8. So if we just omit the box function, then we can write n minus 1 is equals to 7 into 8 means 56, which will implies n is equals to 57. So there are total 57 peoples are there which have, if there are total 57 pupils, then we can say at least 9 of them will have the same birthday in the same day of the week. Now next question is find the minimum number of students in a class to be sure that 6 of them are born in the same month. So now this one is the similar problem which already we have done. That's why this is the do by yourself question and do the answer, write your answer in the comment box. So I'm not going to do this question. Not only this one, I'm giving you 2 more questions and I'm just eagerly waiting for your answers. So the next question is how many people 1,20,000 are born at the same time? Same time means hour, minute, seconds all are same. To do this question, I am giving you one hint. The hint is minimum number of people born at the same hour. If you want to calculate, then it is n minus 1 by 24 because in a day there are 24 hours plus 1. So accordingly you can calculate the number of pupils they have the birthday in the same hour. Now using this result you can go for the minute calculation. After that, using the result of minutes you can go for the second calculation and ultimately you will find out the number of pupils which have the exactly same time of birth. So you just try by yourself and give me the answer in the comment box. So next question, one more question is there. The question is suppose we have 27 distinct odd positive integers, all less than 100. So that there is a pair of numbers whose sum is 102. What if there were only 26 odd positive integers? So this one also do by yourself question. of inclusion and exclusion. So the statement, the inclusion-exclusion principle is a counting technique which generalizes the familiar method of obtaining the number of elements in the union of two finite sets A and B. Symbolically, we express it as cardinality of A union B is equals to cardinality of A plus cardinality of B minus the cardinality of A intersection B, where A and B are two finite sets. This expression, I hope you can identify. Yes, we come through this expression in the time of probability. Here, just one thing which you can remember, instead of two sets, if there are three sets A, B and C, then the formula can be extended in this way. Here the cardinality of A union B union C is equals to cardinality of A plus cardinality of B plus cardinality of C, then minus of cardinality of A intersection B minus cardinality of B intersection C minus cardinality of C intersection A, then plus of the cardinality of A intersection B intersection C. Another thing which again should be noted, that if A, B and C are pairwise mutually disjoint, then the cardinality of A union B union C is equals to A cardinality of A plus cardinality of B plus cardinality of C. That's all. Now, here the one related problem of this principle of inclusion exclusion. So the question is, how many integers from 1 to 100 are multiples of 2 and 3? So how many integers in between 1 to 100 are there with the multiplicity 2 or 3? So the first set we consider here as the elements 2, 4, 6, 8. In this way it is up to 10 because all these elements are the multiple of 2. So in between 1 to 100, total 50 such elements, so that we can say the cardinality of A is 50. Similarly, the B set contains those elements which have the which are the multiple of 3. So the elements are 3, 6, 9, in this way up to 99 is the element. And here total 100 divided by 3 means 33 is the integer whole number. So the 33 elements are there in the set B. Now, one more set we are going to consider, that is A intersection B. That means the elements which have the multiple 3 and 4. A intersection B is the set where the elements are with which are the multiples of 2 and 3 both. So 2 and 3 both means definitely all the elements should be the multiple of 6. Hence the cardinality of this one is 16, and that we will find out by dividing 100 by 6. So now we will find out these three. So hence, using the principle of inclusion exclusion, the total number of integers in between 1 to 100 which are the multiple of 2 or 3 is this formula A, that is the cardinality of A union B is equals to cardinality of A plus cardinality of B minus of cardinality of A intersection B. So that one is 67. Now, one similar question I am giving to you, which you should do by yourself. So the question is, consider a set of integers from 1 to 210. Find how many of these numbers are divisible by 3 or 5 or 7. Also indicate how many are divisible by 3 or 7 but not by 5. So this one is the similar to the previous question. Using the inclusion exclusion principle, do it by yourself and give the answer in the comment box. I am waiting for the answer of yours. Now, another question, which one is a very much important question from this section. So the question is, determine the number of integer solutions of the equation x1 plus x2 plus x3 plus x4 is equals to 24, where the condition, first condition is given, xi is greater or equals to 0, where I from 1 to 4. That means x1 greater equals to 0, x2 greater equals to 0, x3 greater equals to 0 and x4 also greater equals to 0. Second condition is xi greater than 0, not equals to sign is there. The third condition is x1 and x2 greater than equals to 3 and x3, x4 greater than equals to 5. One more condition is given, x1, x2, x3 greater than 0 and x4 lies in between 0 and 20. So, if this one is the situation, then for each situation we are supposed to determine the number of integer solutions of this given equation. Here, just one thing you should remember, that if the equation of this type x1 plus x2 up to xn is equals to some value, some integer value n, where the initial condition is given xi, all xi's are greater than equals to 0, then the number of integer solution is always, n is the total number of variable, this capital N is the integer value, then minus 1, c is the combination n is this n. So this is the formula. So now by knowing this formula, now we are going to solve this equation according to the given situation. So the first situation is what? The given equation is x1 plus x2 plus x3 plus x4 is equals to 24. So here capital N is equals to 24, small n is equals to 4. Therefore the number of integer solution is n small n plus capital N minus 1 c capital N. So it is 4 plus 24 minus 1 c 24. If we simplify, then we will find out this one, which is the solution. Just remember, here the condition is given xi greater equals to 0. Now next situation. In the next situation, it is given the condition is xi greater than 1. If xi greater than equals to, xi greater than 0. If xi greater than equals to 0, then just the previous way we will do. But as it is xi greater than 0, that means it will imply xi should be greater than equals to 1, which will imply xi minus 1 is greater equals to 0. Now we consider xi minus 1 is another variable as yi. So that means x1 minus 1 is equals to y1, x2 minus 1 is equals to y2, x3 minus 1 is equals to y3 and x4 minus 1 is equals to y4. After considering this one, we will find out x1 is equals to y1 plus 1, x2 is equals to y2 plus 2. Similarly the remaining. Now if we substitute x1, x2, x3, x4 in the given equation, then we will find out the reduced equation as y1 plus y2 plus y3 plus y4 is equals to, here it is 24 minus 4, because for each this substitution we will get 1, 1. So according to this adjustment we will get it 20. So now this is our new equation where we can say yi's are all greater equals to 0. Hence the number of solutions are now small n is equals to 4, capital N is now 20, then 4 plus 20 minus 1 is equals to C20 is equals to, it is 23 C20. If we simplify, then we will find out this one. So now it is the third situation. So the third situation where it is given that x1 is greater than is equals to 3, x2 is greater equals to 3 and x3 greater equals to 5 and x4 greater equals to 5. So that we can write as x1 minus 3 is greater equals to 0, x2 minus 3 greater equals to 0, x3 minus 5 greater equals to 0, x4 minus 5 greater equals to 0. So now if we replace this one by y1, this is by y2, this is by y3 and this is by y4, then we can substitute for x1 is equals to y1 plus 3, x2 is equals to y2 plus 3, x3 is equals to y3 plus 5 and x4 is equals to y4 plus 5 in the given equation, and after this substitution we will get this one, and after simplifying we will get y1 plus y2 plus y3 plus y4 is equals to 8. So here each yi we can say is greater equals to 0, hence the initial basic condition we will find out, and the solution is 4 plus capital N means 8 minus 1. So 4 plus 8 minus 1, C8. If you simplify, we will get it is 165. Now the last condition. For the last condition, the given condition is x1, x2, x3 is greater than 0, not greater equals to 0. And x4, it is greater than 0 and simultaneously less than equals to 20. So according to the situation, we just divide this condition set into two conditions. In the first condition, we consider all x1, x2, x3, x4 are greater than 0. And in the second condition, we consider x1, x2, x3 greater than 0 and x4 greater than 20. So according to the first condition, we can write xi minus 1 is greater equals to 0. Hence, by replacing by yi, if you substitute, then we will find out this equation just as the question number B. So now, if you simplify, then we will get this one. That we know we already done in the problem number B. Next, for the second condition, we will find out that x1 minus 1 is greater equals to 0. Similarly, for x2 minus 1 greater equals to 0 and for x3 for greater equals to 0. And one more condition is, here it is, x4. Now from condition number 2, we will find out xi minus 1 greater equals to 3. For I is equals to 1, 2, 3 it will be. So that can be replaced as yi greater equals to 3, where y1 is equals to x1 minus 1, y2 is equals to x2 minus 1, y3 is equals to x3 minus 1. And the last one is x4 minus 21. It is greater than 20. So if you want to make it greater than equals to 20, then greater than equals to, that means our condition should be greater than equals to. So if you want to make it greater than equals to, then it should be 21. So for it is x4 minus 21 is greater equals to 0. Hence y4 is x4 minus 21. Now if you replace accordingly, then we will find out y1 plus y2 plus y3 plus y4 is equals to 0. Therefore, the number of solution is 1 definitely. Hence, the required number of solution is what? That is the solution for condition number 1 minus the solution for condition number 2. Hence, we will find out the entire solution for this condition. So, accordingly, if you do so, then we will find out it is 1771 minus of 1. So, the answer is 1770. Now, one question, which is the do by yourself question for you according to the previous problem. The same type of problem is here and it has to be solved by you peoples. So the question is, use principle of inclusion and exclusion to find the number of solutions of the equation x1 plus x2 plus x3 is equals to 18, where x1 lies in between 0 to 5, x2 lies in between 0 to 6 and x3 lies in between 0 to 18. So I am waiting for the answer. Thank you. In this video lecture, we discuss about recurrence relation. Here we discuss certain kind of recursively defined sequences an and their solution. The sequence an is simply a function whose domain is the set of natural number. Otherwise, the set of natural number which includes 0 also. So consider a sequence which begins with the number 3 and each of the following terms is found by multiplying the previous term by 2. That means here we consider a sequence which starts with 3 and all the next consecutive terms are multiplied by 2. That means 3 into 2 is 6, 6 into 2 is 12, 12 into 2 is 24, 24 into 2 is 48, and so on. It can be defined recursively by a0 is equals to 3, a0 means the first term, and an is equals to 2 into an minus 1, where n is greater than equals to 1. That means when n is equals to 1, that time we will find out a1 is equals to 2 into a0. a0 is 3, hence a1 is equals to 6. When n is equals to 2, then we will find out a2 is equals to 2 into a1. a1 is equals to 6, hence a2 is equals to 12, and hence so on. Otherwise, we can also define it by a0 is equals to 3 and an plus 1 is equals to 2an. Instead of an is equals to 2an minus 1, we can rewrite it as an plus 1 is equals to 2an. Both are same. That time n has to be greater or equals to 0. Now look, when n is equals to 0, then we will find out a1 is equals to 2 into a0. So we will get 6 for a1. Similarly, when n is equals to 1, we will get a2 is equals to 2a1. a1 is equals to 6, hence a2 is equals to 12, and so on. In fact, the formula an is equals to 3 into 2 to the power n if we can write, then it gives us the nth term of the sequence without calculating any previous terms. If an is equals to 3 into 2 to the power n is given, then nothing requires to define. Here you just substitute the value of n and you will get the consecutive values. For example, if n is equals to 0, then you will find out a0 is equals to 3. When n is equals to 1, you will get a1 is equals to 3 into 2, that means 6, and so on. So, hence the equation an is equals to 2 into an minus 1, or equivalently an plus 1 is equals to 2an, where one term of the sequence is defined in terms of the previous terms of the sequence, is called a recurrence relation. So we come to know what is recurrence relation. So depending upon this formula, we can find out some more things on the recurrence relation. So if we continue with the same example, this one, then from here we can say that the equation a0 is equals to 3, which gives a specific value to one of the terms, is called an initial condition. The function an is equals to 3 into 2 to the power n, which gives a formula for an as a function of n. This one is called a solution of the recurrence relation. So there may be many sequences which satisfy a given recurrence relation. For example, if our recurrence relation is an is equals to 2 into an minus 1, no initial conditions are given, then we can assume that the sequence values are 1, 2, 4, 8, 16 likewise. And if we consider here 7 is the value, then the value, that means a0, if we consider 7, then the consecutive values are 14, 28, 56, 112 and so on. So all such solutions form the so-called general solution of the recurrence relation. On the other hand, there may be only a unique solution to a recurrence relation which also satisfies given initial conditions. For example, if a0 is equals to 3, that means it yields only the solution 3, 6, 12, 24, 28 when the recurrence relation is an is equals to 2n minus 1. So, this is the way by which we can form the recurrence relation. Now, our target is to solve this recurrence relation. Solve means our requirement is to find out the solution of this type. Any recurrence relation can be expressed in the form of only n. So this is the solution part of the recurrence relation. In our consecutive lectures, we will find out that how to construct a recurrence relation and to find out its solution. In this lecture, we come to know about the linear recurrence relation with constant coefficient, how it looks like and what are the methods by which we can solve such kind of recurrence relation. So, a recurrence relation of order k is a function of the form an is equals to phi an minus 1, an minus 2 up to an minus k, and one more term is n, where the nth term an of a sequence is a function of the preceding k terms an minus 1, an minus 2 up to an minus k. In particular, a linear kth order recurrence relation with constant coefficients is a recurrence relation of the form an is equals to c1 into an minus 1 plus c2 into an minus 2 up to ck into an minus k plus f of n, that is a function of n, where the c1, c2, ck all are the constants, where no ck's are equals to 0, and fn is a function of n only. So now linear, first of all let us know what is linear. Linear means there are no powers or products of the ai's, and the constant coefficient is what? Constant coefficient means the constant c1, c2, ck all are constants and not dependent on n. So now one more thing that we should know, that is what is homogeneous recurrence relation. If this function fn is equals to 0 in the given recurrence relation, then the recurrence relation is called the homogeneous recurrence relation. Otherwise, it is called the non-homogeneous recurrence relation. So, if this one is the recurrence relation where if fn is not present, then this is called the homogeneous recurrence relation. And if this term is present, which is the only function of n, then it is called the non-homogeneous recurrence relation. Whatever be it, the homogeneous or non-homogeneous recurrence relation, if we want to solve such kind of linear recurrence relation with constant coefficients, then we are using three basic methods. One is the iteration method, second one is the method of characteristic roots, and the third one is the generating function method. In our next lecture, we discuss all these three methods one after another. We are discussing here the iteration method first. In this method, we find out a general expression of an in terms of n by repeated use of recurrence relation. The method has been described with the following example. So now it is given, solve the recurrence relation an is equals to an minus 1 plus 2 where n is greater or equals to 2 with the initial condition a1 is equals to 2. So it is given that an is equals to an minus 1 plus 2. So we mark it as the equation number 1. Now if we put n is equals to n minus 1 in this equation, then we will find out an minus 1 is equals to an minus 2 plus 2. Now this value of an minus 1, if we substitute in this equation instead of an minus 1 this place, then we will find out an is equals to an minus 2 plus 2 then plus 2. So after simplification we will find out an is equals to an minus 2 plus 2 into 2, because here 2 plus 2 means either 4, so we can write 2 into 2. This is we marked as the equation number 2. Next we put n is equals to n minus 2 in the given equation 1, that means in this equation again. So after substituting n is equals to n minus 2 in equation number 1, we will find out an minus 2 is equals to an minus 3 plus 2. So substituting this value of an minus 2 in the equation number 2, hence we will find out an is equals to an minus 3 plus 2 into 2 into 2 according to the equation number 2. So if you simplify, then we will find out an is equals to an minus 3 plus 3 into 2. So substituting n for n minus 3, n minus 4 dot dot n minus k minus 1, we will find out an is equals to an minus k plus k into 2. Now for k is equals to n minus 1, that means if we substitute k for n minus 1, then we will find out here an is equals to k is equals to n minus 1, so n cancels, so it is a1 plus of n minus 1 into 2. If we simplify, then a1 we substitute 2 as it is the initial condition and its value is 2. So next it is 2n minus 2. If we simplify, then we will find out it is 2n. Hence, we will find out an is equals to 2n. So an can be expressed completely in terms of n. So it is the solution of the given recurrence relation. Let us go for another example. So let the given recurrence relation is an is equals to 2n minus 1 plus 1, where n is greater or equals to 1. And the initial condition is given a0 is equals to 3. So remember here in the previous equation, here our n starts from 2, but here it starts from 1. Simultaneously, initial condition they are given a1 is equals to 2 and here it is started from a0. So that is the reason, as it is started from a0, that's why n is here greater or equals to 1. Anyways, so how to solve this one? So given recurrence relation is an is equals to 2n minus 1 plus 1, that we can mark as equation number 1. Exactly like the previous one, we replace n by n minus 1 and we will get an minus 1 is equals to 2 into an minus 2 plus 1. Now this value of an minus 1 we substitute in the given equation number 1 in the place of an minus 1. So after substitution, we will get an is equals to 2 into 2 of an minus 2 plus 1, then plus 1. If we simplify, we will find out 2 square an minus 2 plus 2 plus 1. That we mark as equation number 2. Again, replacing n by n minus 2 in equation number 1, we get an minus 2 is equals to 2 into an minus 3 plus 1. This value of an minus 2 we should substitute in the equation number 2. And after simplification, we will get an is equals to 2 to the power 3 an minus 3 plus 2 square plus 2 plus 1. That is marked as the equation number 3. So in general, we have an is equals to 2 to the power k, an minus k plus 2 to the power k minus 1 plus 2 to the power k minus 2. In this way, it will continue up to 1. So now if we substitute k for n, then this equation, previous equation becomes an is equals to 2 to the power n. When n is equal, k is equals to n, then it becomes 0. So a0, then plus 2 to the power n minus 1 plus 2 to the power n minus 2 and hence so on. Now here it is, if we simplify, then we should substitute a0 for 3 as it is the initial condition. Then the remaining part is same. After that, now we will find out that except this first term, the remaining all terms are in GP series. So GP series, this is a finite GP series with total n number of terms. It will start from 2 to the power 0 and it will ends at 2 to the power n minus 1. So total n number of terms are there and the common ratio is 2. Hence, its solution is 2 to the power n minus 1 divided by 2 minus 1. Now if you simplify, then you will find out it is 2 to the power n minus 1. 2 minus 1 is 1. So 3 into 2 to the power n plus 2 to the power n minus of 1. If we add these two, then we will find out 4 into 2 to the power n minus 1. So 4 means we can write 2 to the power 2. So after simplification, we will find out 2 to the power n plus 2 minus 1, where n is greater or equals to 1. Hence, the solution is an is equals to 2 to the power n plus 1 minus 1, where n is greater or equals to 1. So one more example for the same kind. So solve the recurrence relation an is equals to 2 into an minus 1 plus 3 to the power n, where n is greater or equals to 2 and the initial condition is given a1 is equals to 3. So for its solution, again in this recurrence relation, we substitute n for n minus 1 and we will get an minus 1 is equals to this one. So this value of an minus 1, if we substitute in the equation number 1, then we will find out the simplified form as an is equals to 2 to the power 2 an minus 2 plus 2 into 3 to the power n minus 1 plus 3 to the power n. This is equation number 2. Again replacing n by n minus 2 in the given equation number 1, we will get an minus 2 as 2 into an minus 3 plus 3 to the power n minus 2. And if we substitute this value of an minus 2 in equation number 2, then equation 2 becomes an is equals to 2 to the power n. Within bracket we substitute this value, then plus 2 into 3 to the power n minus 1 plus 3 to the power n. After simplification we will find out 2 to the power 3 into an minus 3 plus 2 to the power 2 into 3 to the power n minus 2 plus 2 into 3 to the power n minus 1 plus 3 to the power n. So in general, we will find out an is equals to 2 to the power k, an minus k plus 2 to the power k minus 1 into 3 to the power n minus k minus 1 plus 2 to the power k minus 2 into 3 to the power n minus k minus 2. In this way, it will continue and we will find out 2 into 3 to the power n minus 1 plus 3 to the power n. Now, if we replace k by n minus 1, then we will find out 2 to the power of n minus 1 a1, 2 to the power n minus 2 into 3 to the power 2, 2 to the power n minus 3 into 3 to the power 3, and hence so on. Hence, by substituting a1 is equals to 3 as it is the initial condition in this above equation, then the equation becomes a1 for 3 we substitute, and simultaneously what we will do, we take 1, 2 as division, and as we will take this 2 extra, then here it is 2 to the power n minus 1. So instead of that we should write 2 to the power of n. Similarly, from the next term we can write 3 square is there, so we can divide it by 2 square, so that we can write 3 by 2 its whole square. And here if we want to adjust this 2 square, then it has to be 2 to the power n. Similarly, in each and every term, if we adjust accordingly and we write 3 to the power 3 by 2, then we will find out here 2 to the power n all the time, and it is 3 by 2 its whole cube. Then next it is 2 to the power n 3 by 2 whole to the power 4, and so on. So now if we take common 2 to the power n 3 by 2 from each of these terms, then we will find out 1 plus 3 by 2 plus 3 by 2 its whole square, and so on. It is up to n minus 1. This is a GP series with common ratio 3 by 2, which is greater than 1. So its value is 3 by 2 to the power n minus 1 divided by 3 by 2 minus 1, and 2 to the power 3 into 3 by 2 is common. So if we simplify, we will find out here 2 to the power n, then 3, here we will find out 1 by 2. So this 1 by 2 is cancelled out, and it is 3 by 2 to the power n minus 1. Now 2 to the power n, if we take the LCM, then we will find out 3 to the power n minus of 2 to the power n by 2 to the power n. So this 2 to the power n and this 2 to the power n cancel out. So after this cancellation, we will find out 3 into 3 to the power n minus 2 to the power n, where n is greater or equals to 2. And hence this is the solution for this recurrence relation. So now one thing for you, that is the do by yourself question. So one question, here 2 questions I am giving to you. If possible, try to solve this out by yourself and give the answer in the comment box. Here the first equation is an plus 1 is equals to an plus 3, where n is greater or equals to 1 and the initial condition is a0 is equals to 3. And the second equation is an is equals to 2 into an minus 1 plus 5 to the power n, where n is greater or equals to 1 and the initial condition a0 is equals to 1. Now it is the second way to solve the recurrence relation, and the way is method of characteristic root. By this method, we can solve homogeneous linear recurrence relation and non-homogeneous linear recurrence relation. So for linear homogeneous recurrence relation of degree k with constant coefficient is of the form an is equals to c1 an minus 1 plus c2 an minus 2 plus dot dot ck an minus k. If n term is absent, as it is the homogeneous form, where all the c1, c2, 3, ck are the real constants and ck definitely not equals to 0. So if you want to solve such kind of solutions, such kind of recurrence relation, then initially we substitute an is equals to r to the power n and let it be the trial solution. Then this equation number 1 becomes, instead of a1 we substitute r to the power n. So it is r to the power n is equals to c1 r to the power n minus 1, as it is a n minus 1. then C2 r to the power n minus 2 and so on. So it is Ck r to the power n minus k is the last term. So now divide this entire equation by r to the power n minus k, so this last term, and rewriting we will get r to the power k, then minus of, we just write all the terms here in the left hand side. So it is minus of C1 r to the power k minus 1 minus of C2 r to the power k minus 2 minus dot dot, at is lastly it is minus of Ck is equals to 0. That we say as the equation number 2. So this equation is called the characteristic equation of the recurrence relation. So now after getting this relation, we can solve this relation. So as this is the power of k, so there are total k solutions. If k is equals to 2, then we will say this is a quadratic equation, hence we will get the 2 solutions only. So if k is equals to 2, then we will get the 2 solutions only. So on that situation, there are 3 basic rules we will find out. So the first rule is, if the 2 solutions are R1 and R2 and these 2 are not equal, that means 2 different roots you will find out and both the roots are real roots, then we will have the recurrence relation, its solution as an is equals to a into r1 to the power n plus b into r2 to the power n, where a and b both are the constants. Next rule is r1 is equals to r2. That means both the roots are same. That one we can say as r. Then an is equals to a plus bn into r to the power n is the general solution. Next, if r1 and r2 are the 2 roots which are complex conjugates, such as r1 we can say as r into cos theta plus I sin theta and r2 is equals to r into cos theta minus I sin theta, then its solution is an is equals to r to the power n a cos n theta plus b sin n theta. This is called the general solution, where a and b are definitely with a constant. One more thing, if it is k value is not 2, if it is 3, 4 or 5, anything, then if you solve as the power is k, you will get total k number of different solutions. That solutions may be, some of them are equal, some of them may be the different real and some of them may be the complex roots. So accordingly, we just punch all these 3 rules. If you will get the 2 different roots, then we will write these 2 values according to the rule 1. If you have, suppose there 2 roots which are same, then we rewrite in this format. They are definitely a and b. This constant becomes c and d. And if the complex roots are there, then we will write according to this one. So this is the method by which we can solve the recurrence relation for the homogeneous system. So one real-time example is, suppose an is equals to 3an minus 1 plus 4an minus 2, where initial conditions are given as a0 is equals to 0 and a1 is equals to 5. So now by the characteristic root method, if you want to solve it, then initially we rewrite this equation as an minus 3an minus 1 minus 4an minus 2 is equals to 0, and that one is termed as equation number 1. So now this one is a second order linear homogeneous recurrence relation, as it is n minus 2 up to. So now if you replace an by r to the power n, then the trial solution of 1, which is, then the given equation becomes r to the power of n minus 3 into r to the power n minus 1 minus 4 into r to the power n minus 2 is equals to 0. Hence we divide this entire equation by r to the power n minus 2. After this division, we will find out r square minus 3r minus 4 is equals to 0, which is a quadratic equation. If we simplify this and solve, then we will find out r have 2 values. One is 4 and another one is the minus 1. So that these 2 are the real values and 2 different values. So rule 1 should be applicable. So the general solution is an is equals to a into 4 to the power n plus b into minus 1 to the power of n. Now we have the initial condition. a0 is equals to 0 and a1 is equals to 5. Now we use these initial conditions to find out these two constants a and b. So when a0 is equals to 0, that means when n is equals to 0, we will find out a0 is equals to a plus b, because this term is 1 and this term is also 1. So a plus b is equals to 0 as a0 is 0. Now when n is equals to 1, we will find out 4a minus of b is equals to 5 as a1 is equals to 5. Now solving these two equations, we will find out a is equals to 1 and b is equals to minus 1. Hence the complete solution is an is equals to 4 to the power n minus of minus 1 to the power n. As it is minus of minus 1 to the power n, so we can write it as 4 to the power n plus minus 1 to the power n minus 1. So corresponding to that, you can solve the equation by yourself. The first equation is an, the recurrence relation is an is equals to 5 an minus 1 minus 6 into an minus 2, where the initial conditions are a0 is equals to 2 and a1 is equals to 6. The second equation is an is equals to an minus 1 plus an minus 2, where initial conditions are a0 is equals to 0, a1 is equals to 1. Try to solve these two questions by yourself and give the answer in the comment box. So one more example where the recurrence relation is an is equals to 4 into an minus 1 minus 4 into an minus 2, where the initial conditions are a0 is equals to 1 and a1 is equals to 1. So for the solution, again we rewrite this one as an minus of 4an minus 1 and plus of 4an minus 2 is equals to 0. So which is again a second order linear homogeneous recurrence relation. If we substitute an is equals to r to the power n, then we will find out this one as r to the power n minus 4 into r to the power n minus 1 plus 4 into r to the power n minus 2 is equals to 0. Now if we divide the entire equation by r to the power n minus 2, then we will find out r square minus 4r plus 4 is equals to 0, which is a quadratic equation. If you solve this one, then we will find out r values are 2 and 2, so which are the same solutions. Hence the rule 2 should be applicable. According to that, our solution is an is equals to a plus bn into 2 to the power n. Now the initial conditions are given a0 is equals to 1 and a1 is equals to 1. According to the initial condition, if we substitute here, then we will find out from the first initial condition a is equals to 1 and 2 into a plus b is equals to 1. If you substitute this value of a here, then we will find out b is equals to minus of 1 by 2. Hence the general solution is an is equals to 1 minus n by 2 into 2 to the power n. This is the solution. So easy, I hope you can understand. So again, for you one question is, that is an is equals to 8an minus 1 minus 214 8n minus 2 plus 18an minus 3. Where the initial conditions are a0 is equals to 1, a1 is equals to 1, a2 is equals to 1. Just mind it that this one is a third order linear homogeneous recurrence relation. Solve this question and give the answer in the comment box. Thanks for watching. In our next lecture, we come to know about the characteristic root method for non-homogeneous recurrence relation. Thank you. This video lecture is the continuation of the previous one, where we discuss for the linear homogeneous recurrence relation by solving by the characteristic root method. Here we solve by characteristic root method the linear non-homogeneous recurrence relation. At first we come to know about the form of the linear non-homogeneous recurrence relation. So this one is an is equals to c1 an minus 1 plus c2 an minus 2 plus c3 an minus 3. In this way ck an minus 1. So up to that it is the homogeneous form. Now if fn is included, then it is the non-homogeneous form, where all these c values are the real constants and fn is the function of non-identically 0 depending on n value. So the solution of this non-homogeneous recurrence relation, if we want to find out, then we will find out it in the two steps. we write an is equals to anh plus anp. So where anh is the solution of the linear homogeneous recurrence relation. That means if we just exclude the term fn from the given equation, then we will find out the homogeneous equation. Its solution is ana. And a to the power p is the particular solution, also called the trial function. So the following table shows different type of trial functions against different specified function fn. So if fn is a constant, a simply constant, then its trial function is a constant. If it is n, which is a linear function, then its trial function is an plus b. If it is n to the power k, which is a polynomial of degree k, then its solution is a0 n to the power k plus a1 n to the power k minus 1 plus ... up to ak. If it is alpha to the power n, where alpha is not a root, then its trial function is a into alpha to the power n. Again alpha to the power n, where alpha is a root of multiplicity m, then its solution is a into n to the power m alpha to the power n. So now, according to this situation, we are going to solve few problems for this method. So now find the solution for the linear non-homogeneous recurrence relation an minus 2an minus 1 is equals to 6n, where n is greater or equals to 2 and the initial condition is given a1 is equals to 2. So for the solution, we at first consider the homogeneous equation of the given recurrence relation, which is an minus 2an minus 1 is equals to 0. Now we know how to solve this equation, because already in our previous video we do how this homogeneous equation can be solved. So here I am repeating the process. An is equals to r to the power n we should substitute, which is called the trial solution. So the given this equation becomes r to the power n minus 2 into r to the power n minus 1 is equals to 0. If we divide this entire equation by r to the power n minus 2, then we will get r minus 2 is equals to 0, which will implies r is equals to 2 because it is the first order equation. Hence, the solution of the homogeneous equation will be a and h is equals to a constant into 2 to the power n. This is by applying rule 1. So now the given specified function is fn is equals to 6n. So the trial solution we know, as it is the 6n, the linear form, so the trial solution a and p is bn plus c. We take the constant b and c here, as a constant already we have taken for the homogeneous part. So now this one bn plus c is the trial solution. So since an plus c is a particular solution to the non-homogeneous recurrence relation, then it should satisfy the equation. If we replace an by bn plus c, then we will get, here the given equation is an minus 2 an minus 1 is equals to 6n. So instead of an, we substitute bn plus c. So instead of an minus 1, we should substitute bn minus 1 plus c. So accordingly, if we substitute, then we will find out for an it is bn plus c minus of 2 into an minus 1 is there, that's why it is b into an minus 1 plus c, and 6n as it is. Now if you simplify, then we will find out from here it is minus of bn plus 2b minus c is equals to 6n. Now if we compare both sides, the like powers, then we will find out n term is here whose coefficient is minus b, and n term is here, its coefficient is 6. So we can say minus b is equals to 6, or we can say b is equals to minus 6. Next, 2b minus c is a constant, and here no constants are there. That's why we can say 2b minus c is equals to 0. As we know, b is equals to minus 6. So if we apply the value of b, then it will imply c is equals to minus 12. Hence, the solution an is a into 2 to the power n, which is the homogeneous part, then minus of 6n minus 12, because b value is minus 6 and c value is minus 12. Hence, this one is the solution, but here still this a is the constant which is unknown. But we have the initial condition. So now we apply the initial condition. It is given that a1 is equals to 2. That means if we substitute n is equals to 1, we will find out a1, which is 2, is equals to, here 2 to the power n means 2, because 2 to the power n, 2 to the power 1. So it is 2a, then minus of 6, n value 1 is only 6, minus of 12. If we simplify, we will find out a is equals to 10. Hence the solution is an is equals to 10 into 2 to the power n minus 6n minus of 12. So now one more question is there. So the question is, solve the recurrence relation an plus 4 minus an is equals to 2 to the power n. Here no initial condition is given. No initial condition means for the homogeneous part, whatever the constant terms are there, that will remains as a constant. We have no option to find out the specific value for those constants. So now consider the homogeneous equation at first, that is an plus 4 is minus of an is equals to 0. Again we replace an by r to the power n, which is the way by which we can solve the homogeneous recurrence relation that we know. So accordingly we will find out r to the power n plus 4 minus of r is equals to 0. That will implies here r to the power n. So if we divide it by r to the power n, then we will find out r to the power 4 minus 1 is equals to 0. Its solutions are plus minus 1 and plus minus of I. So the modulus and amplitude form of I, we know this is cos pi by 2, then plus minus of I sin pi by 2. So the general solution is the homogeneous form for ANH is, here the 4 solutions we will find out. 2 are the real and the different, and 2 are the complex roots we will find out. So we will write corresponding to 1 plus minus I 1, we will write a into 1 to the power n plus b into minus 1 to the power n. Then plus of, here it is 1, so it is 1 to the power n, then c cos n pi by 2 plus minus d sin n pi by 2. So let the trial solution is a n p is equals to c1 2 to the power n, because we know if the alpha n is the given function, then its trial solution is constant, some constant into alpha to the power m. So that it is c1 is a constant into 2 to the power of n. Now substituting this value in the given recurrence relation means in the given recurrence relation this one. If we substitute, then we will find out c1 2 to the power n plus 4 minus c1 into 2 to the power n is equals to 2 to the power n. Now if you simplify, then we will find out c1 2 to the power 4 minus c1 into 2 to the power n is equals to 2 to the power n. Now comparing both sides, we will find out it is c1 2 to the power 4 means it is 16 c1 minus c1 means 15 c1. So 15 c1 means is equals to 1, the coefficient. So c1 is equals to 1 by 15. Hence the solution is an is equals to, these are the 4 terms which we will find out from the previous, and now it is 1 upon 15 into 2 to the power n. So that's all for this. So in our next lecture, we go for the generating function method, that is the last method of the recurrence relation. Thank you. This is the final method for the solution of recurrence relation. The method is generating function method. A generating function for a numeric sequence a0, a1, a2, ar up to infinity is defined as an infinite series. And the series is a0 plus a1x plus a2x square plus in this way it is up to infinity, which we can sum up as summation r from 0 to infinity ar x to the power r. This one we say gx, which is called the generating function. For example, gx, if the numeric sequence is 1, 1, 1, that means all the terms are 1. So that one we can define as 1 plus x, because a1, a0, a1, a2 all are 1. So that we can substitute here 1 plus x square in this way up to infinity. So that we can write as summation of r from 0 to infinity x to the power r, which is 1 minus x to the power minus 1, or 1 divided by 1 minus x. That one is the gx, the generating function. Similarly, another example for gx for the numeric sequence 2 to the power 0, 2 to the power 1, 2 to the power 2 in this way. That means a0 is 2 to the power 0, a1 is 2 to the power 1, a2 is 2 to the power 2, and hence so on. So that the generating function gx becomes 1 plus 2x plus 2 square x square plus 2 cube x cube. In this way it is infinity. And if we summing up, then we will find out 2 to the power r x to the power r, which is the infinite series whose expression is 1 minus 2x to the power minus 1. So that we can write it as 1 upon 1 minus 2x. One more example, that is gx for the numeric sequence ar, where ar is 2 into 3 to the power r, where r is greater or equals to 0. So ar is equals to 2 into 3 to the power r means, and initially we should write down as the summation form. So it is r from 0 to infinity, 2 into 3 to the power r, that is instead of ar, then x to the power r. Now if we substitute consecutively r from 0, 1, 2, 3, then we will find out this series, infinite series. And its simplified expression is 2 into 1 minus 3x to the power minus 1. That we can write 2 divided by 1 minus 3x. One more example. So if the numeric sequence is 1, 1, then 1 by 2 factorial, 1 by 3 factorial, and hence the all. That in fact 1 by 1 factorial, and it is 1 by 0 factorial. So now if we define it by the generating function, then we will find out gx is equals to summation of r from 0 to infinity 1 upon r factorial x to the power r. So this is the expression, and this one is nothing but e to the power of x, that we know. Now some important series and their generating function. Actually what happens on infinite series is there, we know. According to this infinite series, we can find out an, and after getting all this, we can find out gx. So if 1 plus x square, this one is the infinite series, that we can sum up as summation r from 0 to infinity x to the power of r, where x lies in between minus 1 and plus 1. So here an definitely 1, and its generating function is 1 upon 1 minus x. Similarly, if it is alternatively plus minus, then we can sum up it as r from 0 to infinity minus 1 to the power r x to the power of r. So its an is minus 1 to the power n, and its gx is then 1 divided by 1 plus of x. Similarly, if it is 1 plus 2x plus 3x square plus 4x cube in this way, then its summation is r plus 1 into x to the power of r. And its an, then we can say it is n plus 1, and gx is 1 upon 1 minus of x, its whole square. Next one is 1 minus 2x, that is alternative of this one, sign 1 minus 2x plus 3x square minus 4x cube in this way. Then its series is minus 1 to the power r, r plus 1, hence the an, and the gx is, instead of this minus, it is the plus. These things you will understand if you go for the binomial theorem, which I have already explained in the discrete mathematics lecture number 5. So you can go on that lecture for the more precise expression, or for more precise finding of this series. You will find out that how we will get this one and corresponding an and its corresponding generating function. Next, if the series is x plus 2x square plus 3x cube, then you will find out so, where an is equals to n and gx is equals to x divided by 1 minus x square, and so on. Here some more series for your reference are given. These are some standard important series which you may require to solve the coming problems on generating function. So hope you can check it. So now let us begin with the example. So the first example is use generating function to solve the recurrence relation an is equals to 3an minus 1 plus 1, where n is greater or equals to 1 and the initial condition is a0 is equals to 1. So here the given recurrence relation is an is equals to 3an minus 1 plus of 1. So at first we convert this an into the form of summation an xn, that means x to the power n. That's why we multiply this equation by x to the power n and take the summation from 1 to infinity. Remember, we can't take it from 0 to infinity, because if we take it from 0 to infinity, then that one we will find out in the negative, which is not possible. That's why we sum it up from n is equals to 1 to infinity to get all these indices positive. So if we do so, then we will find out from here an xn. So an x to the power n, then summation of n from 1 to infinity. Then 3 into summation of n from 1 to infinity an minus 1 into x to the power n. Then plus of summation n from 1 to infinity x to the power of n. Now, this one if we write n from 0 to infinity, that means what? We will write, when we substitute n is equals to 0, then we will find out a0 into 1. So that is a0. So that term we will write extra here. That's why we take the minus of a0 to adjust this one. So now if we write summation of n from 0 to infinity an x to the power n minus a0, then it is equivalent to this one. Then is equals to, here if we take 1x out, that means if we write 3x, then summation n from 1 to infinity, then it is an minus 1, and x to the power n minus 1, then we can write. Similarly, here from also we can take 1x out, and the remaining we write summation n from 1 to infinity x to the power n minus 1. Now this one is nothing but gx, because gx we know that is the summation of n from 0 to infinity an x to the power of n. So that it is gx minus of 1. 1 means a0 is given 1, the initial condition. That's why we write it as 1 is equals to 3x. Then this part is nothing but gx. Here it will be started from 0. That's why it is an x to the power n. It will be started from n minus 1 and n is equals to 1. So that this one is also gx. Next it is x, for it is x, and this one means as it is n is equals to 1, it will start, and x to the power n minus 1 is given. So it is equivalent to summation of n is equals to 0 to infinity x to the power n. So that is nothing but 1 minus x whole to the power minus 1. That we know from the standard formula. So now if we simplify, then we will find out gx. We just keep all the gx one side. So gx minus of 3x gx. This one we will take in this side, so that it is 1 plus x divided by 1 minus x. So now if you simplify, then we will find out gx is equals to 1 upon 1 minus x into 1 minus 3x. So that 1 upon 1 minus x into 1 minus 3x can be expressed in the form of a divided by 1 minus x plus b divided by 1 minus 3x, where a and b are the constants. So now that can be written as a into 1 minus 3x plus b into 1 minus x is equals to 1. So that time these two parts are cancelled. That means we just take the LCM of this part and we cancelling after this one, we will get this equation. Now if in this equation we substitute x is equals to 1, then we will find out this part is 0. And for x is equals to 1, we will find out minus of 2a is equals to 1. Hence a is equals to minus of 1 by 2. Now again in this equation, if we substitute x is equals to 1 upon 3, then this part becomes 0. So that we will find out 2 by 3 into b is equals to 1, which will implies b is equals to 3 by 2. That means this expression can be rewrite as, instead of a we should substitute minus of 1 by 2, and instead of b we should substitute 3 by 2. So it is minus of 1 by 2 1 minus x inverse and plus of 3 by 2 1 minus 3x its inverse. So this one means it is the summation of n from 0 to infinity x to the power n, and this one is summation of n from 0 to infinity 3 to the power n x to the power n. So now if you compare both sides, then we will find out summation n from 0 to infinity a n x to the power n, the value of gx is equals to, we can take half common from these two, and at first we write 3n x to the power n into 3, that means 3 to the power n plus 1, this one. then minus of 1 into xn. If we compare both sides, then we will find out an is equals to half of 3 to the power n plus 1 minus of 1. Hence, an is equals to 1 upon 2, 3 to the power n plus 1 minus 1, where n greater than 0 is the solution of the given recurrence relation. One more example, let us check the example number 2. So, the given recurrence relation is an minus 7 an minus 1 plus 10 an minus 2 is equals to 0, where n is greater than 1. And the initial conditions are a0 is equals to 3 and a1 is equals to 3. So, we know that the gx means it is summation n from 0 to infinity an xn. So, accordingly, the given relation, the recurrence relation in this, if we multiply by x to the power n and take the summation over definitely from 2 to infinity, as it will ended up to n minus 2. So that after doing this one, we will find out the equation as summation n from 2 to infinity an x to the power n minus 7 into summation of n from 2 to infinity an minus 1 x to the power n plus 10 into summation n is equals to 2 to infinity an minus 2 x to the power n is equals to 0. So now this one will imply, if we write instead of 2 it is 0, then an x to the power n definitely we can write, and we write two terms extra. One is a0 and another one is a1x. That's why we subtracted these two. Now it is minus 7. Here we take x outside to make it an minus 1 x to the power n. But still it is started from 2. And we should make it from n is equals to 1. So if we do so, then definitely we write a0 extra. And here we take the x square outside. That's why we write it an minus 2 into x to the power n minus 2 is equals to 0. So that will imply this one is gx. a0 is given 3. a1 is given also 3. That's why we write minus 3 minus 3x. Then minus 7x. This one is gx. a0 is 3. Then 10x square, and this is gx. Now if we simplify, then we will find out gx is equals to 3 minus 18x divided by 1 minus 2x and 1 minus 5x. Again we should express this one in such kind of forms. How to express in this way? So that one we can write as a divided by 1 minus 2x plus b divided by 1 minus 5x. So now if we take the LCM of this side, then we will find out a into 1 minus 5x plus b into 1 minus 2x is equals to 3 minus 18x. So if we substitute x is equals to half, then this part is 0 and we will find out minus 3 by 2a is equals to minus 6, which will imply a is equals to 4. And if we substitute x is equals to 1 by 5, then this part becomes 0 and we will find out 3 by 5 into b is equals to minus of 3 by 5, which will imply b is equals to minus 1. So now if we substitute a and b values here, then we will find out the expression in this format. So that we can write 4 into 1 minus 2x its inverse minus of 1 minus 5x into its inverse. So gx means summation n from 0 to infinity an x to the power n is equals to 4 into that one we can write summation of n from 0 to infinity 2 to the power n x to the power n. And minus of this one for we can write n from 0 to infinity 5 to the power n x to the power n. You just check for this solution. It is the important series which is given in the table format. So that one if we simplify, we will find out that xn if we take common, then 4 can be taken inside. So 4 means 2 to the power 2. So we can write 2 to the power n plus 2 minus of 5 to the power n into x to the power n. Now comparing both sides, we will find out that an is equals to 2 to the power n plus 2 minus of 5 to the power n, where n is greater or equals to 0. So this one is the solution of the recurrence relation. I hope you can understand. So if you understand, then for you there are few questions to solve. So the first question is an minus 9 an minus 1 plus 20 an minus 2 is equals to 0. Where n is greater or equals to 2 and the initial conditions are a0 is equals to minus 3, a1 is equals to minus 10. The second equation is an is equals to 4 an minus 1 minus 4 an minus 2 plus 2 to the power n, where n is greater or equals to 2 and the initial conditions are a0 is equals to 1, a1 is equals to 4. One more question is given, that is an minus 5an minus 1 plus 6an minus 2 is equals to 2 to the power n plus of n, where n is greater or equals to 2 and the initial conditions are a0 is equals to 1 and a1 is equals to 1. Solve these three questions by yourself. Question is this one. Here it is an minus 5an minus 1 plus 6an is equals to 2 to the power n plus n, where n is greater or equals to 2, and it is given that a0 is equals to 1 and a1 is equals to 1. So if you want to solve it, then initially we know that gx is equals to summation of n is equals to 0 to infinity an x to the power n. Now the given recurrence relation is this one, which we can mark as number 1. Now multiply the recurrence relation 1 by x to the power n, and summing from n is equals to 2 to infinity, we have this one. Here we take it x to the power n, we multiply by x to the power n because we want to need this type of function, and we summing up from 2 to infinity because it is given that n is greater or equals to 2. Now after this summing up, we will find out, like here this is summation n from 2 to infinity an x to the power n, because here it is the an given. Now it is the minus of 5, then summation of n from n is equals to 2 to infinity an minus 1 x to the power n. From here it is this one. Now 2 to the power n for 2 to the power n x to the power n, summation from n from 2 to infinity, and likewise for n it is n into x to the power of n, then summation of 2 to infinity. Now as it is given from n is equals to 2 to infinity, we should convert it to the n from 0 to infinity. But if we write so, then we have written two terms extra. One is when n is equals to 0, that is a0, and another one is when n is equals to 1, that is a1 into x. So we have to subtract these two. Now it is the next one, it is the n from 2 to infinity, this one for, we should write it from n from 1 to infinity, because it is given that a n minus 1 from. So accordingly one extra term we have written, so that is a0, and which we should subtract. Next it is the 6x square of this one. Here no term will be extra, but as n from 2 to infinity is here, that's why we should take x square common. Similarly here from also we take x common, so that it becomes x to the power n minus 1. So now that one is equals to, here again this one is from 2 to infinity, so we should make it from 0 to infinity, and for that reason we write two terms extra, that is for n is equals to 0 and another one for n is equals to 1, so that we subtract accordingly. And from this term we should write it from n is equals to 1 to infinity, and accordingly we should write here, and one x should be taken out, so that this one is our, so after summation we will get this one. Now we just write down, instead of summation of n from 0 to infinity an x to the power n, it is gx. So gx minus 1 minus x, because a0 is equals to 1 and a1 is also 1, so that this one now minus 5x, it is gx minus of 1 because a0 is 1, then 6x squared and gx, then this one is equals to, we should write here this one from generating function table, which is you will find out in lecture number 13, where you will find out the generating function method. One table is given there. If your an is 2 to the power n and this one is your given series, then that we can write as 1 minus 2x whole to the power minus 1, then minus of 1 and minus of 2x. Then plus of x remains outside, and instead of this one it should be 1 minus x to the power minus of 2, and it is minus 1. After that if we simplify, then we will find out, look, then we will find out it is all gx had been taken in one side, so it is 1 minus 5x plus of 6x squared gx, then minus of here from it is minus 1, then minus x, then minus of 5 plus of 5x. So it is completed, and from here it is, we should write of 1 upon 1 minus 2x, then plus of, from here it is x divided by 1 minus x its whole square, then it is minus 1 minus 2x, and from here it is minus x. So finally, if we simplify this one, then we will find out gx is equals to this one. Just have a look how to solve. All the steps are done here. So just a simplification. We take the factorization from here. Then we should take it in this side and take the LCM for the entire thing and simplify. So finally we will get gx is equals to 1 minus 8x plus 27x square minus 35x cube plus 14x to the power 4 whole divided by 1 minus x its whole square, 1 minus 2x its whole square, 1 minus 3x. So now this function 1 minus 8x plus 27x square minus 35x cube plus 17x to the power 4 whole divided by should be splitted into this 5 factors. A by 1 minus x square plus b by 1 minus x plus c by 1 minus 2x its whole square plus d by 1 minus 2x plus e by 1 minus 3x. Now from here we are supposed to find out the value of a, b, c, d and e. So now how to find it out? Though this part is not necessary for this problem, but still I am giving you the solution how to find out a, b, c, d and e. After that I come back to the question again. So now if we take the LCM for the entire this thing, then we will find out this part. So here in the LCM, whatever we will find out as a factor, left hand side and right hand side both the factors are there, so that this becomes cancel out. Hence we will find out this part is equals to here. Now if this one is said to be the equation number 2, then in this equation if we put x is equals to 1, then we will find out that except this term all the terms are 0, because 1 minus x such factor is there. When x is equals to 1, then which terms belongs to 1 minus x, this factor all are vanishes, except that this term, the first term, all have contains this 1 minus x. So if we substitute x is equals to 1, then we will find out from here a is equals to 1 by 2. Similarly, when we substitute x is equals to 1 by 2, we will find out the value for c is equals to minus 2. Then when x is equals to 1 by 3, then we will find out the value for e, which is 17 by 4. Now when x is equals to 0 we substitute, then we will find out from the equation number 2 that b plus d is equals to minus 7 by 4. Because we know the value of a, c and e already, we should substitute these values in this equation. So we will get the another equation, let it be 3, in terms of b and d. And similarly, if we substitute x is equals to minus of 1, then we will get one more equation in terms of b and d, which is 36b plus 24d is equals to minus of 27. We should term this one as equation number 4. Now if we solve this equation number 3 and 4, then we will find out the value of b and d. So while we are solving these two equations, so this one, from this equation if we multiply by 24, then it becomes 24b plus 24d minus of 42. And in this equation we multiply by minus 1, so that we will get minus of 36b minus of 24d is equals to plus of 27. If we solve, then we will find out b is equals to 5 upon 4. Using this value of b, if we substitute in the equation number 3, then we will get d is equals to minus 3. Hence, if we substitute all those values of a, b, c, d and e, then we will find out gx is equals to this one. So now by substituting all those values, we will find out gx is this one, and now here we are in the situation to convert it to the generating function. So gx means we know it is summation of n from 0 to infinity a n x to the power n, 1 upon 2 1 by x, 1 upon 1 minus x its whole square, that one can be written in this way. You will find out this one in the table given in the lecture number 13 for the generating function method in the discrete mathematics part. Now for this term we will find out this one, this term we will find out this term, and for this one we will find out this, and for this final one we will find out this one. So after that we just take the xn common from all those and we write the entire remaining portion here. So after simplification we will find out that an, if we compare on both sides, then we will find out an is equals to this one. Where n should be greater or equals to 0. And this is the solution of the recurrence relation. Hope you will understand, and if any such questions you will find out, then try to solve by yourself with very careful manner. I hope you can able to solve all the questions regarding this topic. Thank you.